Okay, Rajan.
Happy New Year to all. Yeah, thank you, Christopher. Happy New Year to all of you. This is our New Year specials.
It's Happy
And
New Year.
briefly, myself and Christopher were discussing about the European conference. We are kind of started uh, putting for a room. It's called Dean's Budapest. We hope to get some meeting rooms there. Essentially, it'll be a meeting, be one of the first meetings for our techs that will eventually become World University. And subsequent years or even after 6 months, we can think of going to a different place. But this will be a good place because it seems to be quite it's reasonably affordable. Uh, Christopher already have booked a room there. So we are inviting those who are interested to let us know. It will be a meeting. It won't be a full conference or anything to start with, but we'll be launching that. So it will be in Budapest, Hungary, uh, typically May 28th to June 2nd. That's the present schedule that we have. We don't have any specific agenda, but as the time goes, we will evolve into specific agenda. But we plan to uh, host a live meeting, and that way people can ask questions if necessary. We are trying to arrange for that, and we can live broadcast to our text like this one on YouTube, StreamYard, and that way everybody will know what's happening. uh, and that we start to launch our very first conference, so to say, at Budapest. So thank you very much. We'll look forward to seeing you. We'll have more information as we go along. So let me now
It's
move
great.
on to presenting my ongoing research. There are like three or four different areas. This is one of them. I
Okay.
mentioned about
Yeah.
previous one on the on the time conservation. This is a next step. Uh, what we are measuring and is the signal to noise. So essentially, we get signals from outer space. This is the information that we get normally. We don't get any other information. We gather information through telescopes or radio astronomy or right now LIGO, the gravitational observatory. So the gravitation waves you can measure. We totally measure cosmic microwave background. These are the information we get, and from telescopes we are interpreting what that is. So the biggest question is about the from Newtonian classical mechanics onwards. The question from of gravity that Galileo found is the one that is really uh, difficult to a theory or model on. So right now we are thinking about quantum gravity because we are quantum mechanics that had proved to be useful in solving the ultraviolet catastrophes. Excuse me, and now we are into vacuum catastrophe with quantum mechanics and the relativity not agreeing with the vacuum energy aspects. So we have explored from Emmanuel onwards very fundamental understanding of the point physics, and then with Christopher worked very closely on many different areas. Uh, and what I found from my point of view, Christopher is his own hyperspace that we eventually combined with my understanding of the time. When I research about time, I find that a time is not what we see. It's not a scalar time that we see, but it's a wave function, and that has six dimensional, like uh, rank six tensor. We need to describe that. And our previous publications show that we can derive our time from that. Now what I'm doing is in this research, let me go to some figures that we may see a signal like that normally. So we get a signal to noise ratio. Gamma is a signal to noise ratio. And is some coordinate. We don't know. We can make it into space and time coordinate. This is borrowed from chemistry, physical chemistry, where we talk about order of reaction versus a coordinate. We just call it a coordinate. And that seems to be good because generally we don't know what this independent coordinate is. So we get a signal like that. We see a signal like that in any coordinate system. And that can characterize thermodynamic concepts, energy equation, heat capacity, spatial parameters. And then the idea is that we get a tangent plane or what we call as a gauge, which is a differential of that, is what we can measure. Normally, we cannot measure absolute values. So, and that's the biggest problem. So, we get a differential, but we have to know now, we have to fix a coordinate, and what is used in relativity or quantum mechanics is space and time, space time, the megalithic space time. But we don't know the order of the space and the time coordinate. So I'll call it x to the power n, t to the power m, which means it could have any rank or dimensions of that space. Typically, a Euclidean is 3, so we have x, y, z coordinate, and time is only 1, taken to be 1, scalar time. But this is a more general approach. So when I do the differential, I get let me come back to that later. I get a signal like that, and when I feed into uh, a program, so I program this using Python briefly, and get a signal value. This is a normal called a Welch method. So I'm not going to details about that because I have given some details in the in this uh, paper, which works in the Physical Science and Biophysics Journal 2024-82. So we can access this one. And in that one, I describe how this comes about, the power spectral density, which is normally used. And so we can get a power signal density or spectral density versus frequency. So this is the plot that we get. And this plot, it has very similar characteristic that I have found it here. So I'm comparing that. What I'm saying is a very abstract, from very abstract things, we come to a real things. We can come to a real measurement aspect. Because when we start here, we have no idea what these are. But then by using some manipulation, mathematical manipulation, we get a tangent plane and using the time aspect, equations like that I had developed before, how the signal to noise is connected with the wave function aspect. This is the wave function and the characteristics of the wave function, which shows about our hot PDP mechanism of rotation and
Okay.
also
It's nearly time there, Rajan.
Hawking.
Another minute.
Okay, thank you. So
Okay.
again, this is the previous one, shows how we can measure them. So essentially, because I'm trying to put it a brief thing, I'm just giving briefly that we can advance this, and the next one advance it to understand about the particle. So that's the next paper that's going on. I just want to briefly give, and then I will let Christopher ask questions, and
Great.
if anybody has any questions, I can.
Great,
Thank you very much.
So this plot here, is this related to this CMBR, cosmic background radiation?
It's very connected to that. Yeah, it's a general signal that actually feeds both the CMBR. See, when you do both CMBR and gravitational wave, you get a signal like that with discontinuum physics.
Okay, well, don't use too many terms here, but just that is not the CMBR, then, is what you're saying.
This is CMBR. It's a combined CMPR and gravitational wave.
Okay, how are you combining the two though?
It's a general signal, that is any signal measurement, okay? Signal measuring equipment, which measures as a frequency, and then converts the power spectral density.
Wait a second though. I thought the whole thing was that you had signal to noise ratio. So
yes.
what is the signal to noise? Like what is the data you're using?
The data is from the signals that's available. So
what signals?
It samples a frequency. It's a sample frequency.
Okay, it's a random data set. So you're generating you're generating the data randomly.
Yes.
Okay, so what's the signal to noise ratio of a random data set? It's going to be 0, isn't it? Or minus whatever.
No, actually they change. It can be 0, but it doesn't stay the same. It varies with time. So if you put a signal, it varies. It's dynamic.
If you're differentiating over the signal,
yes.
Then so where's your original signal? Where's the original random signal?
Oh, here it cannot show. I can only show schematically. See, I show schematically, and I feed this kind of a signal into that program.
Okay, but that's not a random. That's not a random signal. Where's the random? Where's the randomly generated signal that you created?
Yeah, I feed that and then ask.
Where you need to answer the questions. You need to answer the question.
Yeah.
Okay, so I'm confused. You generated a random signal, yeah?
Yes.
Then you take the signal to noise ratio of that, and is that how you get this plot here?
No, this is my generation.
How did you create that signal? What's the data that you're analyzing to create this signal?
This signal, this is my from what I get it. I get it from the normal. If you go to the images of signals, you get different patterns of signals, right?
What do you mean the images? What images?
So if you put a image of a typical signal, it will generate a signal. It will generate a signal, different patterns.
I don't understand. What's an image of a signal?
Signal versus in time, how a signal varies with time. So I researched about how signals vary with time.
What do you mean how signals vary with time? What are you talking about? That's very general. Do you mean what kind of what? I don't follow any of this, Raja. I'm sorry.
Okay. If you have an oscilloscope, right? If you measure a signal from oscilloscope, an oscilloscope outputs signals, right?
Okay. So I follow you there. Yeah, you're able to you alter the frequency and the amplitude, the wavelength, and it outputs a signal. So that's kind of what you're doing. You're generating a signal based on frequencies. Wait, is that it? Okay, so where are those signals? Why haven't you included them in your research?
Well, I have many different signal patterns created over a period of time. Okay, then I studied them.
And then I studied them. What do you do? Do you take the signal to noise ratio of the signals?
Yes.
Okay, why? Why are you doing that?
Because to
if it's a pure, sorry, Rajan, if it's a pure signal that you're generating, like a sine wave on an oscilloscope, that's not going to have any noise in it, is it?
It is not. It is input from a sensor. See, you have signals.
What sensors are you using?
Okay. I was in a place, and they were able to put a sensor to measure any type of signal. So you put a very
okay, but are you using that information? You're not using that data either, though. So I'm just curious, what data are you using?
No. Different data. I mean, I look at very different data of signals.
Okay. This graph here that you have on screen shows signal to noise ratio of some signal, and all I'm asking is, what is the signal that you are analyzing?
Okay, there can be thermodynamics, heat for heat signals.
No, but what is the signal? Where is the data coming from? Is it from an oscilloscope? Is it from a sensor? Is it from space? Is it the CMB, or like you're just not telling me anything? I don't know what any of this is. You're not saying what it is.
It is because I study a pattern. You see the signal patterns over very different patterns. Like, what are the common patterns in thermodynamics? If you measure for that heat, what is the pattern of the signal that is useful, that's concerned for a heat, right? So if you measure temperature, for example, temperature over a period of time, right? That's one of the signals, and you get a large dynamic pattern there.
You're talking in very abstract terms. I want to know what.
Yeah.
So you're dealing in abstractions here. So these are like.
Yes.
Okay. So this is like a placeholder for actual data that's actually being analyzed.
Yes.
Okay. So let's move on then.
Okay. So one says that.
We move on past all this as well, because we don't need to discuss any of this. Keep going. And so this is not actually it. You've taken, what was it again? The differential of our original. No, wait a second. You took a differential of the abstract form, and then you use the Welsh. What's that? Welsh.
Yeah, Welsh.
Method.
I have it here. This is normally used. Example using Welch's method. Welch's method is a popular approach for estimating the PSD.
Oh, sorry, what's PSD again? Oh, the power spectral density.
Power spectral density.
Now, so that's not related to Planck's law, is it?
No. It's much more general than that.
Oh, okay. So it's not quantum. Okay. You're saying
it's not quantum. It need not be quantum. No.
Okay.
There's no assumption of quantum or anything. Right. It's just a signal analysis. That's it. Very simple.
Can you explain it to me? Because I don't know what it is. Okay. Power spectral density. So it's about the power of the signal, is it? The density.
Power spectral. Yeah, power spectral density is the density of the signal. Always density measurements are much better than the total measurement. We have to know the area.
Okay, you're going to have to slow down. What does that mean, the density of a signal?
Okay. It talks about analyzing the frequency content. The frequency content of the signals.
So okay, what is that? What is that? So yeah, you're analyzing the different frequencies. So would you not use Fourier transforms?
Fourier, yes, it does use Fourier, yes.
Okay.
It uses FFT.
So what's FFT. Next? What's the next step then?
Okay, so the signal processing then. Okay.
So I just want to know what the Welsh method is. Like, what does it mean?
All right. So the procedure for the Welsh method is we are going to divide the signal into overlapping segments, about 50% overlap.
Okay.
Then using a window to each segment. You use a window for each segment.
Yeah.
Then you compute the fast Fourier transform each window signal, and then calculate all the squared magnitude. So the
Okay.
square is the power.
And what are you summing those?
Average the squared magnitudes and normalize by sampling rate and Windows energy.
Right. Okay. So that's what you did. And then do you just use, right. So what did you use? Oh, you import Welsh from SciPy-Signal.
Yes.
And then you want to put your signal in, which is the random data, and then the sampling frequency, so 1,000. And then what's this n per? Oh, this is the window size, is it? N per segment.
Yes. Yes.
So 256 was your window size, and then you plotted it, and so the results you get are the power spectral density of the kind of abstract data that you had previously differentiated.
Yes.
So this is more of, I think this is more of a method, is it, Rajan, than an actual?
Yeah, exactly. Yeah. Okay. It's more a method than in specific things. Yes.
Right.
It's more of a methodology.
So what did you say the next step was? You want to work with real data, is it?
Yeah. So what I did was I used this one for converting from our PDP to a real particle. So that's the next paper.
But wouldn't you want to do this again with like actual data from, you know, the COBE spacecraft or LIGO?
Yeah, we can apply that eventually. But I'm saying is that
the next step, because you created a method now. Now would you not want to prove it on the actual data so that you know if the results are correct?
Yeah, that will be a next step. Yes. Okay. So,
but how do you know
the next one?
What would the power spectral density of the CMBR look like?
I have not plotted yet. I have to plot that.
No, but surely, have they already plotted this? Have you looked it up?
I have not seen any, but I have to look more. I have to research more.
Power spectrum of the CMBR. Search the web there. Power spectrum.
Okay.
This is quite a
good point.
Yeah.
Power spectrum.
There it is. That one at the top there. Yeah.
This one, right?
Yeah, that figure there. Not that one. No, not that one. Not that one.
This one?
No. There. That one. So that is what you need to recreate. But sure, they already have it, so why recreate it? It already exists.
Yeah, so you compare this with that. That's the idea. So compare with the abstract thing.
Okay, but if you compare it, it would want to look exactly like that, yes? In order for it to be correct.
So I have to adjust things
if you get it so it's exactly like that, you basically shown your method is equivalent to their method. Correct?
Yes. No. But I will, since this abstract thing, I will know the coefficients, the actual values, which is not in this one. In here, it's just an analysis of an experiment that's there. But there, it comes to fundamental parameters. So I know the fundamental, what's the value of the fundamental parameters, which goes into getting this value. You see that? So the background parameters.
Also, if we look at the bottom here, it's got multipole moment on the x-axis, where I think you have frequency. Yeah. If you look at how this graph is created for the CMBR, it's incredibly complicated what they've done.
Yeah.
For you to recreate this from scratch is likely going to take, I just don't think, I don't know if it's possible, but if it is possible, it's going to take you a long time to do. Now, if you want to combine this signal with LIGO signals or something, I don't even know where you're going to get this gravitational wave data from. But let's assume you have it. You would have to first show that your method works to regenerate this. Then you'd have to show. I don't know. I wouldn't. I don't think this is a valid sort of. I don't think this will be fruitful for you. Let's put it that way. If you go down this route, I don't see what the end point of this will be. And yeah, I mean, it's interesting. I like that you're using these methods like power spectrums, Welsh. It's very a lot of signal processing. It's pretty cool. It's all based in your sort of background, isn't it? But then
yeah.
It just the rest of it, you know, Rajan, just like where it's going, why you would be combining CMBOR data with, I don't see why what the point of it is. Yeah.
The reason I'm doing is because the quantum gravity thing, like you said, I'm going to present about the M brain, you know, the M theory next week. And so I looked into that. Quantum gravity. And the quantum gravity is not, the problem is the quantum gravity is not, you know, it does, there are a lot of things that's missing. So I'm trying to see whether you can fill up from the abstract thing and then, you know, the fill up.
Yeah, I don't think that's going to work. I don't, like, well, you see, I already have a theory of quantum gravity. And what's the other one? Just, you know, that sort of joining
loop quantum gravity.
Yeah, not that though. Yeah, string theory is another one. Yeah, I suppose next week you're going to do brain, M brains, and all that.
M theory, yeah, maybe M theory. What?
Yeah, but that's research that's already been undertaken decades ago. Yeah, and has basically gone.
Just it's a history.
I know. Yeah, I know. But so that's and it's also kind of hasn't really panned out, but it's perfectly fine. But yeah, no, I don't know. I just think maybe how do you say this? Well, it doesn't really matter. Like, you know, I kind of have my own sort of. I think you were there with Emmanuel, and we have the theory of quantum gravity. So surely, like like I've got up to that point. Surely, with you being aware of how far the research has gotten, would you not say, "Oh well, we could say, oh, Christopher has gotten to this point, and then we'll just build off that instead of starting from scratch again," or what do you think?
The reason is that, okay, so that's, I want to get to a point where you can combine. I think the next paper, I don't know, we had time to show that. That's under peer review about the particle thing. When the particle thing happens, I'll briefly show if it's possible.
Yeah, go ahead.
Okay. So let me pull up that. I will stop sharing. Let me pull up that first. What I have put in. Okay. I think I may have this manual.
So is this new paper related to the other paper you were showing?
Yeah, these are all these have some continuity because I built up based on that the next one. Okay, it's like a step function.
How does it connect, like, to what you just showed?
Okay, it's like a step function. So let me show. I mean, everything should be. I mean, I have put in this
No,
one
but
is in the
I just,
research page now.
yeah, like, how does it connect? Like in a sentence or two, how is this new research connected to your old research? Just in a sentence.
It's signal to noise ratio. Yeah, defining the signal to noise ratio.
That's not a sentence. That's just a couple of words. I just want to know, how is it connected to what you're showing?
It is connected through transforming the signal to noise ratio and the domain into the domain that we measure.
Transforming the signal to noise ratio into the domain
that we are able to measure.
But aren't we able to measure it if we're transforming the signal in the first place?
Because we depends on the domain of measurement, the signal to noise ratio will change.
Okay, I don't follow. But no, anyway,
suppose I'm measuring.
It does sound related. You're still in sort of signal to noise ratio territory, but I think this is separate research, isn't it? Sort of.
Yeah,
I'd say sounds like a different one altogether. So maybe do another presentation on this at another stage.
Yeah. I mean, this is now being the final stages, but it will take another week or two to complete that.
It's a lot of work, isn't it?
Yeah.
You've got some outputs. Looks interesting.
See, I use that signal pattern and from abstract, and then I get I manipulate the process that.
Is this more abstract data, or is this real world?
From the previous one, continuation of the previous one. So
okay.
And then I get, this is like a dark matter, how it will look like, kind of schematic. I mean, it's a program. It's all programmed. Now I have programmed everything Python, kind of. So everything it comes up. And now this is the one we talked about, the spin spectroscopy. Here it's just a data. See, I get a charge, right, of all this and the mass. Then I find the E over M, right? So I plot using
I remember this.
Yeah. So this is not my makeup. It's just the data that's available, right?
Yeah.
I just plot it differently. I plot this one versus the spin number, right? So for tau,
wait a second. It shows your spin number there. It's going from 0.4 to 0.5. Is that right? But how is the muon a spin 0.49?
I adjust this with the Thomas precession, because dynamically what happens is, so that's the adjustment.
Thomas precession
I do three things.
Spin too, isn't it?
Quantum relativistic effect.
Relativistic effect, so that. But why does that affect does it affect it due to its mass or something?
Yeah, the Bohr magneton itself, with dynamically, it does affect that moment, the magnetic moment. The Thomas precession affects the spin in a relativistic moving particle. The Compton scattering, high energy, the mass term does not change, but it does affect depending on.
Where's your calculations there showing? Because it's been a while since I looked at the Thomas or whatever session.
Yeah.
How does it work?
I programmed it.
Wait a second. Isn't the whole point of just recap on the Thomas precession thing? Is that not so basically it's saying that it doesn't really do a spin to because it's moving at the speed of light, it slows down. So the time it takes to do one rotation appears to be 2 or something. So how do you get? So you're saying that if you were to undo the relativistic part, you get 0.49 instead of 0.5. Is that it?
Yeah.
Okay. So where's your calculations to show that?
Yeah. So I put in the program because it's so complicated. I started programming these things now. I
Okay.
did some basic calculator with a thing. So I got some, but in order to plot it, I have to program it. So this is
Okay,
the
but
type of program.
where's your equations though, so I can see what you're talking about? Because I still don't understand what you mean. So just looking
So
for the
it puts the
equation.
data.
Okay, yeah, we know the
So,
data. That's fine. I'm just looking for the equations.
okay. So you have.
Is it in there?
I just did
Oh, you shouldn't. By the
scatter,
way,
yeah.
for some reason, Rajan, they say not to put all your code in the papers.
Not all of them. Just an example. One
I don't
example.
think. Yeah, I don't think you should be putting code in papers. For some reason, they say not to do that.
The appendix I added in case somebody want to regenerate.
Yeah,
They can.
I don't know. They just say not to do it. So
Really?
that's yeah.
Oh, because
Okay.
I
Anyway, so
see.
where's your equations? I don't want to look at the code. I want to look at the equations. Unless the equations are in the code, are they?
Yeah, yeah.
Okay, well then show us those. Where is it? That's just.
So you have the.
These are just the plots. We're not interested in that. We want the equations. Oh, is this it? No, it's not. Oh, it is. Random. Hang on, you've got random in there. Random data? Or what? What is this?
Correction factor.
Okay, where are you getting the correction factor from?
The correction factor from the literature, from the data available from the literature of the Bohr-Magneton, Thomas precision. So it loads the data,
right,
and makes a correction factor.
Okay.
Because it's loading.
But then you see your spin plus this correction factor. So how is it possible if the spin of a fermion, let's say, is 1/2, and then you're adding this correction factor? What is the correction factor? What's the value?
It could be positive or negative. It can be positive or negative.
Yeah, it would likely have to be negative in this instance, though, wouldn't it?
A lot of it is negative. You can see that it's negative.
So right. And so you're just getting that from a lookup table or something. Someone else has done the calculation, and you just add it to the spin. Is that it?
Yes.
Okay.
Yeah.
So that's.
I have not done the experiment myself. So
yeah, fair enough. That's interesting. Okay, so what do you glean from all of this? What's the end result?
Okay, so like that, I give only that example, but all of them are coded in that. I have the coding we want that for each of them, each of these blocks with all the things in there, which gives this. So this is one of them for fermions, right?
Cool.
I do that bosons. Same thing with bosons, with the photon, the W boson, and a Z boson.
Okay, now I have a question. I have a question here. They've calculated this as well for bosons, have they? The Thomas precession?
Yes.
Okay. Very good.
So then I have for graviton also this imaginary particle.
Yeah.
What it will look like. Okay.
So it's
and then I put all of them.
Yeah.
So I put all of them together.
Yeah.
So I have a region, the electron, then muon, tau, photon, W boson, graviton, the electromagnetic effect, just electromagnetic effect. I connect this one. Then I have
what is tau
weak
photon?
gravitation.
What is that though? The tau photon electromagnetic effect. I'm not familiar with that.
So the tau, and because it is at the end, so is one of the forms of the electrons.
Right.
And when in the transition, this transition is an electromagnetic effect.
Okay, got you.
So
and then the Z boson graviton with the weak gravitational effect. Okay, and is that okay? And what does that tell you?
Weak gravitation. So essentially, it tells that how the Z boson, how the quantum gravity can come into effect. It's a weak gravity. It's not strong gravity.
But is that
It's
weak?
a weak gravity.
But surely, when you're saying weak gravitational effect, there you mean the weak force and the gravitational force, yeah?
Yeah, the weak force, because C boson is associated with the weak force, right? So,
right. So what is this?
So,
right. So but what does it tell you about that?
It tells you the transition region where the C boson with the quantum gravity, how it can become graviton.
Okay. So scroll down there then. Okay, so you've got yeah, thanks. Got so what's the blue dot again and the graviton? Why is the graviton 2 points? Oh, these are all corrected with the Thomas precession, is it?
Yeah.
Okay, so that's pretty weird, Rajan.
Huh?
Well done.
Oh, yeah.
It's good and weird. I like weird stuff, you know. It's good.
Okay. So I didn't know what exactly you mean by weird, but in a good sense, you are saying.
Yeah, of course.
Okay. Yeah, it is not there before. People are not done this.
No.
So I thought it is very because it will be useful. So I come from the abstract side, right? And you get that, you compare the other side from the experimental side, and you see, you can fill in the gaps and see, is it a possibility of graviton really a meaningful thing? That's what I'm trying to figure out.
Okay.
So this will help in doing that. So electron here, it's an extended, it's an amplified aspect of the quantum relativistic effect. That's it. It's the same thing, but I'm showing here for bosons, and then combine everything.
Right.
So how it will look like. So in a normal plot, how it will look like, you will see only this much. If you do experiment, you will see this kind of displacement. And if you from the experiment using this one, I know the equation or the program. So if I feed into the program and I plot along with the experimental thing, I know what's happening. How the graviton could be created.
Yeah.
How the graviton could be hidden there. It's a hidden variable type of thing, and whether we can measure it and whether it's realistically possible.
Okay, so these are
we don't know yet. We don't know yet. Yeah. Is it a realistically possible thing? This is what we are about to get it. But this is a first step in that. Then after this step, you have to combine with your group theory. I kind of mentioned it somewhere. But this is the final thing. Now, the next step is your thing. You are done extensively, lot of group theory things, and you have come up with the new particles and,
yes.
the chi, and
all of those new particles are they're pretty good, but they are, of course, what's the word? They're like speculative, right? So
yeah,
it seems because there was 8 sort of missing vertices that could be filled in the 24 cell, and there just so happens to be these 8 new particles that are all associated with leptogenesis. So it seems to me that, I mean, I was thinking about this more recently. There was no dark matter particles, but then there was right-handed neutrinos, for example. So but I have a different formulation for the dark matter anyway. That's neither Mond nor dark matter. So yeah, but it is interesting because it's to do with like different densities of space, and then I mean, I think probably density is kind of the key thing here, but
see, I plotted this one, right? It's again pulled up from the literature, but I get this plot of the dark matter. What I call the wave function of the Flamengo. Flamengo is one of the skeletons of this dark matter. So it plots that versus the signal to noise ratio. You get a spread. It's like a noisy spread around the zero dimension, a zero aspect of the wave function, and this shows that it could be a noisy, but it's possible to resolve that in some ways. It's a very high level noise. That's why we see as dark. So we cannot measure anything observable. So it will appear as dark. That's the idea here. So this is again, it pull data and then it plots that. So the program, what you said, what you gave, thank you very much for your the program you gave, because I am using that for a lot of things. And here, I think I have referenced what I said that the next stage, I'm not going to detail, but the next stage will be combining with your thing, because we did support vector machine, right?
Yeah.
And then you have dimension of the hyperspheric universe.
Yes.
Then modified and the 24 cell, especially I like the 24 cell you have.
Yeah, yeah.
Get a 24 cell to the 600 cell.
Right.
You can use that, and the E8 using alternative. So these are the key things I'm saying that will help us to go to the next step. This is my first step. The next step will be yours, because without a group theory, we cannot do anything. It's just a starting point, what I have. But it starts from the abstract level. See, I bring it to the real level, and then your thing kicks in. So
okay, well, yeah, we'll see. There was, I think you definitely, you picked pretty important papers there that I've written. So, like, from my own perspective, like research that I think is, those are probably the most important ones. So good use of references there, and be interesting to see what how it develops then. So I can present a short. We said we do 3 minutes. Was it 3 minutes? I'll have to restore a previous session. Yeah. So I haven't timed this presentation, so I don't know if it will take 3 minutes or not. But to be fair, I gave you 7 minutes, so.
Yeah, take your time. I mean.
Okay, thank you.
Don't worry.
But it's it's not going to be long. Let's put it that way. I don't think it's and like I said, I haven't actually I didn't practice this or anything, so hopefully this won't be that.
It's all right.
And then present. Okay. Send. Share screen. Entire screen. Share. And then. Okay, you can see that, yes?
Yes.
Great. Let's go back to it. Okay, so the title of this presentation is Galois Theory for Systems of Linear Equations, and this sort of the motivation, or the subtitle is an attempt at recreating non-conditional programming, because so that's sort of the motivation to create, a style of programming that is non-conditional. It doesn't rely on if-else statements, and I say recreating because obviously this is work that other people have already done. I know, for example, that different, big tech companies would use mathematical equations to sort of circumvent conditional programming. But I don't know how they go about doing that. So my attempt here is that's what I mean by recreating it, because I'm attempting to do a similar thing. But that's not a huge issue here, because as we'll see, I didn't actually succeed, but I will just show you the research that came from that process and that motivation. So we'll start with a simple system of linear equations here, just 2 equations to start with, nice and easy. And we see x and y as the red line, think, and x plus 2y is the blue line. And so when we solve for the equations, we get y equals 2, x equals 3, and an intercept of 0. So the question is, can we describe this system of linear equations in sort of terms of different modalities or modes of mathematical, concepts, I guess. So, we have a very basic one like a Venn diagram, then things like logic operators, like if, and, or, XOR, those kind of things. So this is where the conditional parts come in, because you have like, if X and Y do this, else do something else. So that's the kind of motivation there. If we can convert this mathematical equation into logic operators that could be used in a conditional sense, and perhaps we could reverse engineer that from the logic operators back to a more mathematical formalism. But we could also go further and describe it in terms of adjacency matrices and then other kinds of graphs, connection graphs. So we start with the Venn diagram, and so we just have the X term here for this circle, the Y, this circle, and 2Y for here. So actually, X is 1, so it's not the entire circle or anything, and Y was 2. So when we have X plus Y, we get 3, but X plus 2Y gives us 5. So it's all very simple, and then all together is 14. So this is the universe that we're dealing with. So it consists of the various terms in the systems of linear equations, so X, Y, and 2Y. And yeah, as we know, Venn diagrams can be expressed as logic operators and or XOR, XNOR, acting on the sets. So this condition could be used to create conditional programming rules without specifying conditions. That's the question. So here we have the, this is X and Y, less X and 2Y, which gives a set of just 2. So we could apply, this is, so we're using logic operators here. So we can recreate De Morgan's laws, which says not X and Y is this set, not X is this set, not Y is this. So not X or Y is the same as this. So that's just De Morgan's laws again. We can see that that's this line here, 154, and this line here, 264. So it's kind of like a V shape. That's the De Morgan's laws there for X and Y in the previous graph. So then I think we can recreate all of this using an adjacency matrix, using X, Y, 2Y, and then we have the terms. This looks like multiplications, but it's not really. These are more like sets. So X and Y, X and 2Y, Y and 2Y, and then we have them on the y-axis here as well. So basically, it's saying, this is the adjacency matrix of the Venn diagram. So X is next to Y, and X is next to 2Y. So but X is not next to X. So that will be a 0 in the adjacency matrix. And I don't think that this term here, which is X, Y, is next to this term, maybe. I don't know, we'll see. X, Y is, okay, so yeah, we see like X is not next to X, but it is next to Y, it is next to 2Y. It's not next to this one or this one. So there's some logic there why X is not next to that, but excuse me, which I'm actually kind of confused about myself why that would be the case. I mean, there's clearly a logic to it, but x is next to y. Okay, so just assuming that that is the correct kind of concept then. And then we have the degrees down here. So there's 3 here, but only there's like 1 here, 1 here. So you just have the degrees of the adjacency matrix are just written below. So then we can turn this adjacency matrix into a graph, and it gives us this kind of form. So we can see, you know, this is x. Let's say it should be written up here, but it's not in a sort of easily digestible form. And it says x is 1, y was 2. So that's correct. So this is x. Y is 2. X. Wait a second. Yeah. And this is y. And then 2y is 4. So they all connect to each other. But then we see that with let's say if we pick 3 here, that was 1 and 2. So that's x and y. So that's this value. And x and y only connects to 2y, which we said was this one, 2. So that's how the adjacency matrix works, and that's how this comes about. So so we see the different degrees then. This would be like the first, I suppose this might be considered the first layer, or this, depending on how you look at it. So there's three degrees in here and only 1 degree of connectivity out here. So we'll move on from that. And then, of course, since we have our matrices, this is our adjacency matrix with the actual values in it instead of just ones. And then we can take the inverse of that. So it's just really messing around. A more complicated example using 3 linear equations. So we have solved for x, y, and z. We couldn't just put these in as matrix, split them into different matrices, and then get the adjacency matrix for those matrices, and we just get back the exact same matrix that we had earlier. But if we don't utilize these matrices and actually just utilize the values, then we'll get an adjacency matrix and graph for the top level that looks like this, and the resulting graph looks like this. So we saw the first one had a very group order, like symmetric group order 3. This one clearly has a sort of a fiveness to it. These are the same adjacency matrices, just well, more of them, and also sort of presented or visualized in a different way using heat maps. So if I'm not mistaken, this first one here is the graph that we just looked at. So this one, although it doesn't look the same, but it is. So I'm pretty sure that this graph here corresponds to this one up here, pretty sure, but it could be this one. The point is, so these are our coefficients up here, and so we can take combinations of these coefficients. So we might take so we take like combinations of 3 and then of 4, or of 2 and 4, or 2 and 3, or 2, 3, and 4. So we're taking, like, we say, you know, it's like this. There's 1, 2, 3, 4, 5. So we say like 5 choose 2, or 5 choose 3, or 5 choose 4, and then create all of those, and then only graph the connections between those different combinations. So this is all the combinations combined. This is just some of them, so that's why we only get like certain, remember I was talking about levels where you have the different degrees of connectivity. So this would be like first degree and last degree. So that's why we get that. But if we were to graph some of the other ones, which are more complicated, which is like, I don't know, first degree, that's first degree and last degree. That's why I'm thinking that one is the other one. But I think this one, so the other one must have been second degree and last degree. And here you have like first, second, and third degree. So we can plot the different levels then. So here's second level, like up to second level and up to third level. What we see is that the graphs become a lot more disordered and a lot more difficult to sort of think about. So if we go back, we could apply group theory to our first system of linear equations, the connectivity graph there. And we notice that there is we can rotate these graphs, and they rotate into each other. So the two-dimensional systems of linear equations, we see that it has a tripart symmetry. This implies that the terms of the system of linear equations can be transformed into one another through rotation, possibly around the intercept at the origin. So as we said, this would be the symmetric group S3 and produces the following unique linear equations. So when we rotate the equations into each other, we get x plus y equals the set xy, x plus 2y, then we get x2y, and y plus 2y equals what, the set y and 2y. And so then we can plot all of those, just using a simple graphing function, and we get these three intersecting planes that all intersect around the origin. And so what we're saying is that, that these can be rotated into one another without any problem. So the question is, how do we rotate them? Do we just use straightforward Euler angles, or Euler angles, as some people pronounce it? And so is it just simple rotation matrices, or do we need to apply the rules that we just saw, sort of permuting the terms within the equations and then just plotting them? That actually I don't have an answer to that yet, because I haven't attempted to do that. But moving on anyway, we'll just look at Galois theory, because obviously everything I've said up to now is very reminiscent of Galois theory. And actually, I think it's a good way of, if you're struggling, as I have been for a long time, to make sense of all of these concepts in Galois theory, then what I've just presented today should, I think, help you kind of understand it a bit better. But I'm not sure if I really go into an explanation of Galois theory in this slideshow, because it was only supposed to be 3 minutes, and I think we've gone way over that time. But basically, you have these extensions for the rational numbers, which are called radicals, and then you can see how you have groups of these. So you have the rational numbers, then you have these extensions, and then you can ask, well, if we combine these two extensions to get a third extension, which is actually the same thing in this case, and you can prove that through various means. But yeah, this is using a different number field with different extensions, and then you just list the powers, and then you get all of the you get a system of equations back, and then you can combine those to create essentially these kind of adjacency matrices, if you like, so you'd have the system of equations up here multiplied by system of equations down there, or at least their coefficients, and then from that, I suppose you could generate these sort of graphs, although they never go to that step, and then you'd be able to visualize provided it didn't go into such chaos as it does here, because of maybe possibly to do with the limitations of the program here that I was using, but perhaps not. And then you can do other things where you you take the vector and you can multiply. You sort of take you can take the inverse of those matrices, then multiply, and then, well, there's some step that you can take, but oh yeah, then basically you take out the terms that you're interested in. So in this case, it would be like alpha and beta, which was our in the original example. This would be alpha, this would be beta, and then you combine the two. Alpha. Well, we have three terms here: alpha, beta, and delta. But you'd combine alpha and beta, and then you go up to 1 to 9, because this creates a 9-dimensional sort of set, if you like. And then you do the powers of those and then print them out. But you're only interested in the alpha and beta terms. So then when you work out the equations for those, you see that they give the same answers. And so you can say that this extension just corresponds to this sort of. So it's like, this is G over here, 1G, and 1F, it's just 1F and 1G. So it's all the same. It's kind of, it's number theory, I suppose. It all seems to just, I think we've spoken about this, it kind of, yeah, it is useful in terms of finding out whether there's going to be solutions, as we mentioned, to the quintic equation. And actually, it shows that there's no solutions for any of those equations, such as the quintic, but also for dimensions 5, order 5 and up. So it's not just dimension 5, as I was mentioned. I seem to suggest that in the previous presentation. So I suppose we can just, I'm not sure, yeah, 5-fold linear equation systems. So going back to our graph here, we see that this also has a 5 rotational thing, 5-fold symmetry. Probably possible up to the first or second layers. So like I was saying, this is layer 1 and this was layer 2. Or disorder of second and third order graphs. Oh yeah, so going back to these graphs here, they're quite disordered for different levels. So that indicates that maybe there isn't really a 5-fold linear system of equations that we can pull out in that sense, because if it is indeed disordered, then there is no possible rotation, but it is possible on this layer, the first and second layers. But yeah, and so maybe this disorder is not a result of the limitation of the graphing program, but is actually a disorder, and that is why the quintic equation is not possible, or something like that. But obviously, we're dealing with systems of linear equations here, whereas Galois theory and the likes convert the radicals into systems of equations as well. But they're generally interested in the roots of those equations, which is why it's applicable to the quintic equation. So that's all interesting, and probably, it is probably a much, or well, obviously it is a more practical application than what was attempted here. But obviously, what we were looking for was along the lines of more, I had to say, well, we were going for different ends. I wasn't, when I started this, I wasn't even thinking about Galois theory. I was thinking about non-conditional programming, obviously, as I said. And so then we can graph those equations, these ones here that come out of the, if we take the system of equations that correspond to these transformations through the 5-fold symmetry group, and we do the same thing that we did up here, then we can graph all of those and we get this kind of thing. So once again, this suggests that all of these can be rotated into each other, either through permutations of the terms, as we've shown, which is actually totally correct, or possibly through some sort of rotational matrices as well. And that's it. Okay, so hopefully you're still there.
Yeah,
are you?
good presentation. You have some more things?
No, that's it.
Okay. So interesting. So interesting thing. It's like a graph theory, like an advanced graph theory type of thing you are doing.
Yeah.
Yeah. So I have a simple question. I think if we can put it back, when you
Sure.
saw
Yeah.
the
share entire screen.
it may be simple that but just a solution.
Oh, right.
The first.
Actually, that video there on I think I say galosh theory. When I first read that word, I was like, "What's galosh theory?" And it just stuck with me as almost like a joke. This is quite a good video here, and it explains a lot. I learned quite a bit about it.
From number theory. He's from number theory.
I think it is a kind of number theory, isn't it? So you can see all of the group theory going on there. Well, it's kind of group theory as well. So, and that so it goes on. So I don't know if this is like, it is a good one. I think this explains why. Yeah, there it is. Why there's no quintic formula. Anyway, let's get back to this.
On top we go. I think top of the first slide. Yeah. See, if you say, I don't know why, x plus y is 3, x plus 2y is 5. When you solve it, you get y equal to 2, x equal to 3. But when you put back, that's not a solution.
Oh, sorry. Yeah,
that's just half
right.
of that.
Yeah, no, I think you're right. That's a mistake. That should be x equal to 1, isn't it?
Yeah, and
so that was just an error on my part. I did. Okay. I have the right values here, 1 and 2.
Yeah, you have the right one then. And the same thing when you go here also. I think the next one after that, the following here also. No, not here.
Oh,
somewhere else you have equation.
Here maybe.
Yeah. I think that value. Let's see. That also doesn't.
Yeah, you're right. Yeah. I might need to be 1 or something. I will have the.
No,
that's wrong, isn't it? Oh yeah. So I think I might have. You know what I might have done? I might have changed. I might have changed the. Maybe it's just. Yeah, I might have changed the values somewhere along the way, when I was doing the work. So I'll have to look into that. But yeah, you're right. Those values are incorrect.
When you put the values back, doesn't add up. Okay.
Yeah, true.
It's very new. I mean, I understand some of it, but not all of it. The concept, I think I get it. The concept of adjacency group, right? Group, the graph. That seems to be interesting. What is based on the Venn diagram? What is next to each other? So you are coming back.
Yes.
Next neighbor. So it's very similar to. I think it's kind of like Fermat. It's not like Fermat, but Fermat was trying to do that in terms of the color. Color graphing. He said that Fermat's last theorem says that how the colors next to each other.
4 color theorem where you have like
color theorem, right? It's a color theorem, right?
Is it not the 4 color theorem though?
Yeah, 4 color theorem. So it says that it's very similar concept that next to the adjacency, what it can have next to each other. So if this color is there, that other color is not possible. So you can describe a border based on that.
Yeah, that's
I'm coming with a more abstract thing.
Sorry, go on.
Yeah, I'm coming with a very mind-boggling thing. You may not have time today, I don't know. That I'm coming with understanding based on the traffic, it's very fundamental. The abstract thing I did, right? The next level is understanding. I think Sabine has done this for contact gravity in one of the things, that how we are going, so I don't know whether if you have finished, I can probably briefly show that.
Yeah, I'm finished. Yeah.
What?
Yeah, if you've no more questions. But well, actually, I was going to respond
okay.
to
Let's complete this.
before
Another few minutes. I want.
you go on, sorry, just before you go on to the next point, then I was going to respond to your earlier point about like the 4 group color theorem and the Fermat's last theorem. Yeah, because I read that book. Someone gave me a lend of it. It was pretty interesting, actually. So, and they do briefly mention, or they go into the 4 color theorem in that, and I don't recall how it's related to Fermat. I thought it was a much later kind of problem that someone had. I think it was a conjecture or something. Try and prove that there's no maps that can't be colored with. That you only need 4 colors to color all maps or something like that, so that no 2 colors are the same next to each other. But it is interesting because the whole thing of Fermat's last theorem, which is what, like x cubed plus y cubed equals z cubed or something like that, and I think he was saying that that's or z cubed as we say over here, but you cannot. It's not. I think he said that. Yeah, there's no solution to this equation or something. But his proof was like just written in the margin of some book. It was just like, you can't. This equation doesn't work. He never explained why.
I think he generalizes x to the power 1, x to the power n, plus y to the power n, plus c to the power n. Only valid up to 2.
Yes, that's what we're saying. That's what we're saying. But
he never
derived it. He just scribbled it in a margin of a book. He never showed why that was so. He just said, "This is so," and so it became like almost like a conjecture in a way. So people tried to, like, obviously he knew. Like, if he didn't know, then he would have just asked the question, "Is there a possible solution for this equation?" But he stated categorically, no, there wasn't. So he wasn't. I don't. The implication is that it wasn't a conjecture in his mind. Like, he had the solution, he just didn't bother writing it out. And then it took that guy. What was his name? Was it Weil or something like that? Anyway, the guy who solved Fermat's last theorem just recently using what did he use again? Modular forms and elliptic curves or something like that. And most people don't understand his proof, and it goes on for pages and pages. But I believe it's considered to be correct, but it's far outside my sort of domain of understanding. But the point is, I think, is that Galois theory and Fermat's last theorem are connected in some way through like number theory or whatever, but there's definitely a relationship between the two. Whereas, I'm not sure if the 4 color theory or conjecture or theorem is connected. Probably is in some way, but I mean, you could say modular curves and or modular forms and elliptic curves probably are as well, but maybe not in a direct sense. They feel like their own kind of area of research and study that it seem a bit separate. But I'm sure, like, we're all like, we're in the realm of linear equations here, and that's all that those other things are. That's all that Fermat's last theorem is. That's all that. Well, okay, modular forms generally tend to have complex numbers in them, but that doesn't really matter because Galois theory also includes things like it can include complex numbers or whatever as further extensions to the field. So that's not a problem. But where am I going with that? I suppose is I suppose. My own research here then is obviously related as well, but just in terms of, but it's using systems of linear equations. And like I said, I was just starting out trying to find. I suppose the reason why they're all so related is because trying to find connections between different like what would you call it, subjects in math, like Venn diagrams, logic operators, adjacency matrices, and graphs, and trying to show that really they're all kind of the same thing and they can all be linked together to get results. And in the case of Galois theory, that you get very impressive results because you can prove that equations do or do not exist without actually necessarily having to plug through the entire universe of possible equations and see, oh, that one doesn't work and this one doesn't work, and you'd be there for infinity hours trying to figure it out. So it seems like this method that he has, it does prove useful in that sense. But I'm not sure if what I presented here really has a use necessarily. I don't see a practical use for it, but I think the practical use for it, because it didn't pan out, we didn't actually get non-conditional programming out of any of this, but I think the only practical use that comes from this is the fact that it kind of helps you understand Galois theory a bit better, and that's about it. So yeah,
be used as a diagnostic tool.
Yeah, on some level, maybe there's, but like I said, I don't know any direct practical application for it at the moment. But just more as a pedagogical tool, like so that, because I think when people try and explain, like even that video that I showed you there on YouTube, where it's explaining Galois theory in a very easy manner that's quite easy to digest. When you look at the comments in the YouTube, the YouTube comments, it's basically, I was going to go write like, oh, thanks for this. This is the first time I understood what this is all about. But then I noticed that all the other comments were like just going on like, oh, this seems like, you're starting us off in the deep end. Like most people didn't understand. Well, everyone pretty much didn't understand it. It was weird that way though, because they didn't really say exactly what they didn't understand about. Oh no, well, they did mention what they didn't understand about it, but they didn't say what they did understand. So yeah, but I got the feeling that they were a bit perplexed anyway, and that's perfectly understandable. And so I decided not to contribute my comment because, it's annoying when you're trying to figure something out and then you see someone else's comment where they're like, oh, thanks, I finally understand this now. You explained it so well, and you're like, you're still scratching your head trying to figure it out. So I decided there's no point. But yeah, now I think if one of those people maybe were to watch this video, although I did not make that presentation in any way for like a beginner, but I'm pretty sure you could make a class where you sit down and explain everything as in simple terms, and then by the end of that they would have a better idea, or they'd be more well positioned then to understand Galois theory, I think, and realize that actually it's not really as complicated as it appears. So it's pretty cool. Yeah. Okay, over to you, Rajan. Did you want to share something?
Yeah. So I just want to explain in general that there's a communication thing always, that that I find also sometimes, I try to do like for the kids, and you go off that, it creates confusion. Like we were going well, and then I interrupted you, and then start talking, and you realize, then you said that, yeah, I not finished the thing. So that communication thing is one of the things that always, I may be jumping ahead of time or stepping ahead of the thing without understanding the feedback that the other people, how they, grasp that, and there's a discontinuity, a jump, and that
Yeah.
creates a doctor. So I try to do that even from my when I was explaining, a lot of the classes I used to be very engaged, even in school, but later on I would think outside of that, and suddenly I put that in. People get confused. People say suddenly, what is the connection? So I realized I go back again, like feedback, and go back and forth. Of course, it produces a lot of stress, thing. But then I found that you have to go one to another like algorithm. So I'm trying to find out what is the best way to do that. And now I think we have a way with the IT, all the artificial intelligence, all these put together. And I have used fairly well that the artificial intelligence to edit the things. I mean, you cannot depend on them to create any original things because it is too rambling. But it helps in editing some other things or pulling up some literature and comparing it. It helps in that. So in that way, one of the things if I want to show this one
is not
it's
a
not a
complete
complete
explanation.
So
if
if
you have
you
to
want to
present
present
this
this one,
one,
let me
something
something came on. Okay, so suppose we are presenting. This is one of the first things we can think about. The first one is an audio, right? Audio is what we are talking about, and then people understand. See, I'm trying to understand the fundamental aspect of how the communication occurred. I think it's a very important thing, even for kids. Sometimes I'm able to, some days in class, they understand everything, what I'm saying. Some days they say, I don't understand what you're talking about, right? So I'm trying to see a fundamental way. I talked to somebody uh, in my relative who is also in IT, uh, and I came. So he also very similar to you in that sense, but he's also he has his own things. So if you don't properly connect with that, he doesn't accept any of the things. But then we finally, after we discussed and everything, brainstormed, he said that write down what you have to. And when I wrote down, I think we talked about audio, image, text, video, and the uh, message or communication. Then
Yeah.
he said it makes sense. He does little bit of the artificial. He's a programmer, so he's a fundamental.
Okay.
That
Yeah.
is
You're talking about.
that is
Sorry to interrupt, Rajan, but you've been on about this before. So the audio and video. So that's really you're talking about this. This is going back to this concept of like a sense field or something, wasn't it?
yeah. It comes from the sense. I mean, the
Audio,
previous some of the
video.
previous
Well,
publications.
I haven't finished asking my question. But
Okay.
yeah. So it's about sort of it rather than, it seems to me anyway, that rather than well, actually, you went into this and then you had this sort of group theory thing that then moves into DNA, isn't it? Or chirality. And then because it is a left-handed chiral thing, it goes to DNA, which is generally winds to the left. It's a very good concept. So, although, yeah, okay, so the point being then that, and then because the DNA makes up the living organism, and the living organism is able to see and hear, yeah. Then so you have this sort of ground up concept, physical kind of model of how the senses arise from the basic fields of matter, is that it? So it's
Yeah,
not
actually, you are right. I mean,
it's not a metaphysical theory. It's very much
yeah.
it's a very much a reductive, ground up
Yeah.
kind of physical theory. Although I think it
Yes.
may be a little bit too ambitious to be feasible or correct or whatever. But yeah, so initially I was thinking you meant it in a different way, but no, I think I think it's kind of cool. Actually, it's a pretty good idea. But you know what else? See, when I was thinking about it, I was thinking about it in a that you mentioned in a more metaphysical way, that you were like, all right, I'm not interested in explaining the universe from the point of view of quantum mechanics or anything like that. I'm just going to explain it from our perceptual sort of, how to say, like our experiential view of the universe, that because we see and we hear things and we can touch things, that is actually the ground of the universe, and everything else is an illusion, sort of, you know, like, because we are like everything that we interact with in terms of physics, whether that's through experiment or through actual, you know, like real, like whether it's through tangible physical experiments that we know of, or through ones which are conducted, you know, experimentally using instruments which maybe have a certain level of abstraction, but are nevertheless still a physical result. Like, all of those things are still based on our perceptions. So at the fundamental of everything is our perception. I think that's, you know, maybe that is the key. So you could say, well, instead of reducing everything then to particles, then why not reduce it down to our senses, you know? But the problem with that is that it goes into solipsism, doesn't it? Because we cannot get deeper than our own perceptions, if you like. I think there's a it's not a koan, but it's excuse me, it's a saying by the Buddha or something, where, you know, the guy is meditating and he meditates for a long time, and he realizes it's something like he's looking in the mirror, but then he turns the mirror around to look at the back of the mirror and sees that there's nothing there except a piece of wood, and this disturbs him, like, you know. And so it's the idea of, like, consciousness is the mirror, and then through meditation you're able to, like, turn the mirror around so you can see what's behind on the back, and then you realize there's nothing there, and then this is like a shocking concept, and the Buddhist says not to be afraid of it or something like that. But anyway, I'm not a Buddhist, but just it's just an interesting maybe relationship between the idea that if we are looking for the ground or the fundamentals then of the fundamentals, which we're saying is perception, we try and go deeper than the perception, and we try and say, well, what's behind that? And then we find, oh, there's nothing behind it. So how are we going to write it? How are we going to write an equation for that? How are we going to do anything with that? And the answer is we're not. And that's fine. And the Buddha would say that's all right. I guess is the point he's making. But anyway, the point I'm making, or trying to make, hang on a sec. I'll be back in a second.
Sure.
Okay, what point was I trying to make there, Rajan? I was getting, oh yes, so this is it, right? So you were talking about sense fields for a long time, but then also talking about physical fields. And then I was in church a couple of weeks back, yeah, and there was a woman sitting behind me with her young daughter, maybe like 2 or 3 years old, or 3 or 4, and she was pretty noisy, pretty noisy kid, you know the way when you're in, I don't know if you ever go to church, but you're in church and there's some kid being noisy, and sometimes it can be very distracting, but in this case it wasn't too bad, because she was just like one of these children that was very outgoing and like explorative. So she was like, explore down the pews here and what's over here, and then back to her mom kept like dragging her back, and then so she had her up on her knee or something, and then she climbed up on the pew in front of her, and I was paying attention to the sermon or whatever. I wasn't paying too much attention to them, so I wasn't even like I wasn't looking at them, or they weren't even in my peripheral vision. But at a certain point, I got the immediate sense that the child was now unbalanced, and it was just about to fall onto the ground, you know, like very heavily. You know the way toddlers are? They're at that age where they're kind of imbalanced. They got big heads, and they're just like, wham. And so, yeah, I got the sense that even though I wasn't looking at them, I could feel that the child was now in a position where it was going to fall, and it was going to like smack its head. And the mother obviously knew this as well, because she would be looking at the child, but was able to catch the kid before it fell. So there was no waterworks, and it was fine. But I thought that was a really weird sensation, because I think I've had it multiple times in the past, but was never, but usually because maybe I was line of sight with what I was looking at that was also falling, that I would be able to attribute it to like, oh, the reason why I could sense this feeling of gravity happening to the object is because I'm looking at it and my brain is just filling in the data. You know, it's like saying, well, this is how it would feel to fall. So this is, you know, so it just fills it in as another sense, an extra sensory perception, like a sixth sense. But in this case, I wasn't looking at the person. So it would have all had to be through auditory. And then even then it made the actual sense much more pronounced, a bit like how when you're blind, the other senses become more intensified. And I could really feel like I knew exactly where the child was positioned in the room, and I knew where, you know, how long it would have taken them to fall to the ground, kind of thing, and like how much force was being applied, all of that kind of stuff, but in a very general sense, like or not in a general sense, but not in a quantitative sense, but rather a qualitative sense, which is what our senses are. So I just thought that was interesting as applied to your work. So I think there must be something within us genetically and on a cellular level, and or even beyond that, as we're saying that there could be something, you know, deeper than that in a perceptual level that is keyed in directly to this force of gravity, and that's really interesting, I think. And I think if my kind of hypothesis about the 120 cell and all of that is correct, then that structure, that kind of fiveness, pentagonal dodecahedral structure, and all of that, it has to be related in like we have to be directly connected to that, either on our cell, maybe not on a cellular level, but I think it's more to do with and this probably should be a subject of another presentation at another time, because I can't really go into it. But I think it has more to do with time, and I do have some notes on that. But basically, and I think I tried to present this before years ago, to do with like a circle that is non-Euclidean. So it doesn't just have 360 degrees, but it gains an extra number of degrees. So it becomes like 366 or 367, and then because our universe is Euclidean, it goes up, and then it tries to fill that gap in, and it does that by stretching itself over, and then as it stretches, it pulls everything over with it, and it's that motion then, and that keeps happening, and it keeps going around and around, and that motion is time, and that is how we get time, because of this extra degree of freedom that keeps popping into reality that needs to be covered over constantly. And it's like so small, like it's a tiny effect, but because it's compounded over, like it's happening like every Planck scale or whatever, Planck time as well, and it happens over and over. Then when you build it up, it's like a flick book, and you get, and time occurs out of that. But if the universe stopped filling in those gaps and the circle kept expanding, then we would begin to see the fiveness of the geometry of time. You know, it would go out of the you know, the fourfold crystalline structures we were talking about, and go into the kind of fivefold 120 cell structure, and then you'd be able to see like the whole hyperbolic extent of the universe. And in that realm, then there would be no time, because there's no longer any space for the time to expand, and as we said, the time was just filling in the gap anyway. So yeah, and so there's more to be said about that, then we start getting into like the really kind of metaphysical part, though, where it's like almost like a new conception of what it means when we talk about entropy, because usually when physicists go on about entropy, they say, well, the arrow of time is entropy, you know, and things always move from order to disorder, you know, chaos to.
Is this something you need?
Oh yeah. like chaos or order to disorder, or like even life to death. You know, as you're born young, and then you age, and then you die, and then the atoms in your body then disassociate and go into some sort of disorder. But really, if we think, that doesn't make full amount of sense, because halfway through that process, often people will get together and they will have children. So that is, if you like it, the opposite then. So the time is generated by the addition of hyperbolic degrees of freedom to Euclidean space, which is therefore, i.e. extra degrees of freedom, like we've been discussing. The gauge group that preserves the symmetry of time, or lack thereof, as we just said, because, you know, time doesn't necessarily have a symmetry if it's constantly breaking through this added degrees of freedom. Then, right, so this gauge group that's constantly keeping the universe appearing to be three-dimensional, when, or four if you include time, when it's actually five-dimensional. This gauge group adds or extends itself. So this is what we were talking about. So that creates time, yes. So then degrees of freedom equals entropy, obviously. We've mentioned that. And entropy equals the arrow of time. So there's a couple of notes here about differential equations, which I have to check to see if they're accurate or not, but I'll do that another time. So 4D hyperbolic space is infinite degrees of freedom. That's correct. Once you, if you have the, yeah, there's a couple of different things that I thought. I think you can decrease the angles so that it will have infinite degrees of freedom. So therefore it has no time. And since it has no time, it also has no aging and no death, yeah? But in biological systems, it is the lack of degrees of freedom which leads to death. So I'm saying in this sense that I'm overturning the entropy leads to death argument, but rather I'm saying that, you know, so well, what did I say? Degrees of freedom equals entropy. So that would sound like the more degrees of freedom you have, the more likely you are to die, you know? Because like if your particles are disintegrating, then that's you know, more, they have more degrees of freedom, and that equals death. But I'm saying no, it's probably the opposite way. And it's, you know, in the biological system when it's alive, it is the lack of degrees of freedom which leads to death, i.e. the freezing of limbs, joints, and organs. That's where the organ says, oh, I no longer have freedom, or the joint no longer has the freedom to move, you know, in a direction. Literally lack of degrees of freedom. And that is kind of what causes sickness, illness, disease, death, that kind of thing. And only after death does the disintegration and dissolution of entropy, as is put forward by physics, you know, conventional physics sort of interpretations apply then. So and then if we apply that to like the different ages of man, so we have like when you're a child in your youth, you're kind of more supple, you're more flexible, so you've higher degrees of freedom and therefore higher entropy when you're younger. And then in old age, you're kind of more, you're brittle and you've less degrees of freedom. So that's the argument I'm making there, I guess. I mean, obviously we can go like much further into this. We already mentioned Buddha and his teachings about, you know, the mirrors and looking at the back of the mirrors, but we can also look at sort of more Western traditions. We read the Bible, it talks about how God hardens the hearts of people who he wants to, usually he wants them to fail in some way, so he hardens their hearts, or like because of sin, well, anyway, so let's just put it that way. So, and then also in the Bible somewhere it says the wages of sin is death. So this gives you the idea of like hardening, sin, and then death. So it's all the same thing. And so then the only way to beat death is not to sin, which is obviously impossible. Or the other possible way then would be to add extra degrees of freedom to a circle without, and then the notes stopped there because I got distracted. So, but it's something to do with yeah, if you could add extra degrees of freedom to a circle, without the gauge group coming to close it up again and create time, and you were to add in it like as many as you want, then you would be in a universe where time and depth no longer exists. Okay.
Okay. Are you there? Okay.
Yeah. Yes. No, I finished. So I was.
Okay. So it's interesting. I like it because recently I was talking with Professor Pickering. You know that my mentor. We published that IPC mode. Yeah.
Great.
So he's very old. He's like 89. But normally I send him, every Christmas time I send a Christmas card with New Year. Normally he doesn't respond. Last year he called, like I said before. I think I might have mentioned.
I think
he called suddenly and he said that I am at the top of the list. He was to call. And this year, what happened was because my son graduated, he moved. He is quite interested in that double degree. So he sent me back. That's a very pleasant surprise. It's like he's like the what do you call for me, he's like the like leaving God type of thing. What do you call it? Somebody who I can look up to, and then
an idol,
grow from there. So the thing is that he sent me suddenly. I was in New York, but I saw that he has sent. So when I came back, that's one of the first mail I looked in. He, he's very terse in that sense. He said, "Oh, congratulations, 2 degrees he has. So proud of you. You should be so proud." Yeah, I said I was there. So can you call me? He said that to New Year time. So by the time I came, it's after New Year. So as soon as possible, like I came fourth, I think fifth or sixth, I called him. I think fifth. So it was a Sunday. So he said, I asked, is the right time to call? Yes. I just came from church just now. I go every Sunday to church. I just came in. You called the right time. Then we discussed briefly everything. And I mentioned about you, about our group, and briefly, about my son, what they're doing. So all this like half an hour to 1 hour spent, but briefly everything. He covered everything, update. So I said, we have a plan to have a European conference, uh, you know, uh, and that we will like you to be one of the top, I look upon you as like a godhead type of thing, guiding us all the way. Uh, so he said he doesn't travel anymore. He's in Sarasota, Florida. So he said that you can come and meet me if you want. We can have some tea or coffee. I said we are trying to have World University. We might have we want to probably want to start a chapter in Sarasota, Florida. We want a chapter in each country, but Sarasota, Florida, for example. And at that time we can meet. So I like to meet him. If he finish out. So I said that we are meeting this one, and he said that right now he's not concentrating so much on science because I had done so much, but on religion. He's looking into about the God, about religion, like you mentioned, very similar. So very interesting. I said that maybe the science actually doesn't conflict with the religion or the presence of God itself. He said that's great. Yeah, I think uh, I agree with you, and that you should pursue. So I said, when I become older, I want to get into more religion and philosophy and those kinds of things. But I want to integrate the science, and I say science is not, in conflict. Actually, there is a lot of comparison. You can actually lead That's what I was briefly telling you. I want to go from abstract to real, and then back to the understanding that there should be a creator, and that creator, if you go back, we cannot. How do you argue the Genesis, without a creator? That's the argument I want to get into, and the science. I want to say you can actually fall back if you do it without assumptions. You can fall back and show that actually there should be a creator, because we talk about creator, annihilators, things like that. So there should be a creator, and that creator we call God, and that religion. So it is quite compatible. The two are quite compatible in that sense. So I want to prove that's the case. You can prove fundamentally, even mathematically, maybe very fundamentally, that's actually compatible. The gods, both are not two different aspects. But like you said, that Buddha's thing about the mirror, you cut the back of the mirror, it's totally different. That's consciousness. But then I started thinking, even during the New Year, when I was in New York, Christmas and New Year, I was thinking about the consciousness that all the Nobel laureates also talking about now, Penrose, other people. But I said that, my metrics protocol seems to take me to the final level also. So that's a logical thing that continuously, it gives me information, I process it, and then I can fall back into a graph, things like that. So one of the things that shows that it has what you call the fall. When you fall back, you get the same thing, right? Like you go up, like you said, the circuit theory, like the circle you go around 360, and you get extra thing. It goes to a different dimension, so to say. So it takes up this time aspect. It's very similar. I had an experience that actually the machine consciousness. When I say, so what I do is that message, like machine consciousness. Then I add exactly now things like that. Then I process that information. Then I put in the wave function psi of x. Okay, x the value of you get machines. Okay, because it has an octet structure. I call it octet structure, or like a byte. Byte is 8 bits, right? So each bit is like a letter. So you can only allow 8 letters, and then that 8 letters should make sense to that message. So that's a high level requirement, but I do in my mind, and I found that it is at converging in terms of machine. So there could be a machine consciousness. A machine. This is something a machine can learn. A machine can do actually, because it is algorithmically programmable. So what I am doing. So if I put the artificial intelligence, when it has to go to the next level, then I put the artificial intelligence, machine learning. It can do what I'm doing. It can process that. So I'm sure about that. So sign up that machine, and then I add something else called Arduino, things like that, which is a puzzle I developed in 2023. Again, 2024. It's a huge thing, but that's how I get many other things. So machine consciousness is quite possible, which means that a future machine, like a robot, it could have a consciousness. All it has to read is itself. So when it does that, it reads that, oh, I am a machine. It reads that, it start to have a consciousness, right? So that's how a consciousness works. But then I go beyond that and say, okay, what is body? What is mind? I come to a conclusion, mind is like a firewall. Okay. This is my result. Okay. How I came up with, it's a long discussion, but I'm just saving it the answer is that mind is like a firewall, and body is like a scalar matrix. So it's of a space. So that's why I want to show this one. It's related to that. But like you mentioned, it's quite complex metaphysics, but I kind of understand most of it, what you're saying, because I thought very similarly about metaphysics. I think there is a connection between metaphysics and physics. So, I don't need this. Sorry. I need to project this one. Oops. Add to stage.
All right.
Increase the. Make it solo, like. Oh, you already did. Okay. Okay. So essentially, like I said, the audio is the input, right? So it has the input. How I'm saying that it should work like a feedback circuit. So the audio goes in, and then it creates an image like this graph. Like I mentioned, the metrics protocol says that I can create from the message, I can create an X variable like pictures. This is pictures. If I use my algorithm, this input, throughput, picture, even that, the coding, all that, it is contained in the word pictures. It's like a byte. Okay, each letter is pulled like P, I. So it includes all the first letters of that word. So then it assembles the packages into a word called pictures, which makes sense. Just makes sense to that other that this byte or octet has to make sense to what is there. That's the important thing. So that is the hard part. But it makes pictures, yeah. I mean, if I have pictures, yes, I can do all that, right? Then I measure the signal to noise ratio, which depends on this one. So when I measure that, I get a density matrix called M gamma, which becomes observable when it is Hermitian, which means the conjugate of psi prime when it's equal to this one, when the signal, this M gamma becomes observable. This is the fundamental abstract idea. Okay, it's very abstract, but I'm kind of proving it in one of the ones I showed you, one of the signal to noise ratio, that publication. It is an application of that to IT. Okay, so then you get this one. Then what? Then I say, what is it all about? Time. And why there is time? People, there was a person who was trying to answer the question of what, why. He couldn't answer it. He went around, but he was correct. He was thorough. You want to logically do that. But the why is history because, like Hawking said, brief history of time, right? So if you decode that, you get these values, and then how the physics will explain how that is. So the idea is that eventually you want to have a program and thinking about a program. I think there is a partial program I can think of. Right now it's manual. Maybe you can also help me, or artificial intelligence can help me. This will create a video. That's the idea. The video, like a documentary movie or something, it'll show like a picture, and from the picture, you develop a video. And this video, then you can code it. You can use like a Python coding or something. That code will generate a message which will help continuously help people. Oh, when the message sees people make sense, so they can input their message, then they can interact because people may not understand all of it completely. See, that's what I'm saying, the communication aspect. People may not understand all of this, but when you go through the whole thing and the message comes out, oh, now I know what it is. So then they will reply to it, and then the whole thing starts, and then renew the whole thing. It starts making sense to all of us. That's how it works. It's like a black box, right? Like I proved earlier, black box. So one of the things, interesting thing I found, okay, these are the clocks and things like that. I'm trying to find a table value for this. So one simple thing is how our artificial intelligence is clocks. Then, so when you put this value in, it generates some message. But interesting thing I found is this mesoscopic or traffic thing. Okay, you have a traffic circle here. Now it's a written thing, so I cannot make out what I have written. Sorry, but I want to eventually make it. But I briefly want to show you. Uh, I want to explain that. It's essentially a physics, IT physics. So it's like a traffic circle. So what we did from historically, we started experimental physics, like Galileo, other people. And classical physics was more experimental physics, more observations were there.
Yeah.
But what happened was the ultraviolet spectroscopy all made us. We started moving around this one, and there is some kind of a firewall here. So we moved around the traffic in the 1980s, and then we moved thermodynamics one of the connections. We moved into mathematical physics. This is where Bohr would have come. Bohr, let's say Bohr comes in the motorcycle here. It's motorcycle. He comes here. But when he comes here, he will see Einstein here. Einstein said, then they'll have a conversation here. This is like the Heisenberg concentric principle. So where are you going? Einstein will ask, I'm going to the mathematics. Oh, I'm already coming from there. There are a lot of hidden variables. oh, when I come from there, that's not really true. It's quantum function. So, they have a brief conversation and they will start moving. Bohr will start going to mathematical physics. But Einstein is stuck here because he cannot go anywhere. He's stuck in his car. But when he comes back in the 1960s, you have kind of quantum gravity thing. So the traffic circle continues the theoretical physics like we are done. And then you have modeling and things like that, standard model and that we are also doing modeling. You are doing hyperspace modeling and doing time modeling.
Yeah.
The theoretical physics all come together. Then it moves to 2020. What happens is that that's where I was thinking continuously, with space-time, the space-time aspect. So it comes around and then got astrophysics. Then what happens then, 2040? What happens here? Traffic circle. Now, the explanation is, interesting thing is, the whole thing, I don't know whether you can see that.
Oh, yeah.
Try to, okay. So, the whole thing is like anti-de Sitter space. What happens 2020? The time loop ends, right? My prediction is that this time becomes de Sitter space. So, when you go back and look back, you're looking back at a de Sitter space. And the de Sitter space is almost like a black hole, like event horizon. We are going from event horizon. And you're looking back, you see the reflection of all the things that's happening. It's compressing into that. And you look at the images will show. Okay, it's interesting. Images will show, and we look back, we see that. Then we look forward, we see astrophysical level. And I'm seeing that we may go to Mars or other things, to Earth. The Earth become difficult, hostile environment. Like you see California fires, you know that, right? The heavy things that's happening. So these things are, for me, it indicates that God is telling something that we have to move on. We are probably aliens here on Earth came, and then we have to go back to another place. So we travel to another place. So we are constant travelers. So we have to think further, and then go the astrophysical. But when you look back, this is a de Sitter space. So that's interesting. So all of them come together here.
Well,
like this,
yeah, I don't know. I was just wondering there about the de Sitter space, because didn't they look into that? And you have your model of de Sitter space, but it doesn't fit the universe, does it?
Like, no. This is our part of the universe. It's not a whole universe.
Oh yeah, but okay, all right, okay, yeah, because I've been looking into that. What is it? The turnover of things like you look into space, and everything appears to get smaller and smaller and smaller because it's further away. But then when you get to like around redshift 1. The angular diameter or the angular distance or whatever of the galaxies start getting bigger again. And I thought that's really interesting, and because I'm working on so there's a couple of different things actually that I should probably talk about before that. You have space, and then like let's say it was a closed space, so. Yeah, so omega whatever, omega equals 1. So just to get to the point really here, so you have the antipodal point on this closed space, and they were saying that so that's there's a particle arising there as well, I guess, and that is. That point then, that antipodal point can't really be a point, I don't think. It would have to be a surface of something. But I suppose
depends is it your north pole of your hyperspace, the tangent?
Yeah, this is the thing. North pole? It's very similar to that. It's very similar. So because if you look at the equations, it's got like divided by 1 minus some term. And if that term, the term is the omega lambda coefficient or whatever. So it's to do with the expansion or the curvature. but it's different. So it might be confusing the terms a bit here, but it's that anyway. And when that goes to 1, then you've got whatever your top term is divided by 0, which goes to infinity. So it's this asymptotic point that's not really on the sphere at all. But it is on the sphere, though. That's the weird thing. It wouldn't be on the tangent plane. So basically what they're saying is that for redshifts of very, very large redshifts, the object up there, like the galaxy, is going to be extremely large and extremely bright, which is odd. But it's not just going to be extremely large, but the equation says it's going to be infinitely large, which is a bit strange. So I mean, that corresponds to what I'm talking about a lot. Like you have the antipode is the projective point. So this whole thing about turnaround and projective points, closed universes, which are obviously some sort of 4-dimensional manifold, just represented as a 2D sphere, where the antipode is a singular point, but is actually the boundary of a sphere, which is the particle horizon. Like, you know what I mean by particle horizon? The extent of the observable universe. So I'm using
GERD. Very similar to GERD.
I don't know if those are the correct terms to use. Like they're the correct terms in his work, I mean, but I just mean on a, in a vernacular sense. What's a
metric universe.
Yeah, presumably it's correct, but you get the idea, observable universe. And so I haven't sat down and thought about that geometrically and from a dimensional point of view. Does that make sense? I guess it does if we're looking at the tangent space. We have the tangent space, we have a circle, which is the observable universe, and we project that onto the hypersphere, and that's going to be a circle on the hypersphere. Now, if we were saying that we can't see beyond that or something, so then we project that up to the point at infinity. Why would we do that? I suppose that makes sense. That probably makes sense from one point of view, but I'm not sure that I like it. It feels a bit solipsistic in a sense. It's like, oh, anything beyond the observable universe that we cannot observe does not exist. So the point collapses to a 0 point at the antipode. But I don't really agree with that. I think that if we have the observable universe, and there's obviously a universe beyond that, that those objects are okay. I suppose from a cosmological point of view, like that they're pointing out, those objects wouldn't have a redshift, or they would have a redshift. It's just that the light hasn't reached us yet, and may never reach us because of how they have the recessional velocity. But those objects still have a redshift, and it's going to be greater than the other redshifts that we can observe. And those objects still exist. So that's why I prefer my model, because even though it may have some issues that I'll get into now, but it's because like it doesn't care about the limit of the observable universe, which is just kind of a situation that we happen to exist in because of our circumstances where we are located in the universe, so on and so forth. It would be different for a different part of the universe would have a different observable universe. So this boundary is not really fixed, it's movable. And the point I'm making is that those objects do exist outside that boundary, which is a fictitious boundary in a sense, and they do have a redshift. So you might as well just map everything, and then so that it's pointless then to try and squash all of those things that exist into nothingness at the antipode. Instead say they exist, and the antipode is a real thing that exists above all of those things, and that is the asymptote that exists outside of the entire universe. And that would seems to me to be a better way of going about it. However, there's this turnover point in the universe where, as I said, around z equals 1, the galaxies appear to get bigger. And so I've done a lot of research over the Christmas where I attempted to figure out the size of the hypersphere based on the redshift values. And basically, I was able to build some nice curves, and they're all asymptotes. And I was trying to build a machine that would tell you the distances to those objects. And I was successful in that. So I'll do a presentation on that at some point. However, what I was really hoping for was to find the absolute distance to those objects. What I found was that I cannot do that. So what we have instead is a machine that will tell you the distance to any of those objects, like the absolute distance, but it can only do that with respect to some x value, which is the size of the hypersphere. So the exact thing I was looking for, I couldn't find. Instead, it's like a variable term that you put in and say, well, we think based on some other calculation that the hypersphere will be 60 megaparsecs or something. Therefore, the distance to Andromeda or any object is x flipping, megaparsecs. So, yeah, so as I said, it hasn't been totally successful, and, new stuff has to be done. But, yeah, I don't know. Looking into the current cosmological work, a lot of questions are coming up, and I'm like, yeah, I'm not entirely sure if they're right, but at the same time, I'm not entirely sure if I'm right either, as I'm saying. But hopefully, what we need to find anyway is the bottom line here is that we need to find the correct feature to analyze. It could be that angular distance might be the correct feature, but thinking about it, it doesn't seem like it is. But then maybe you could connect angular feature with redshift and then use that to nail down the size of the hypersphere. But I think even that doesn't work. There's too much like relativity in the equations. Like things can be moved up and down or in and out, and you can get the same answers. So it's really frustrating. And we've been working on this for a while as well. We did the support vector machine work, and that was all. That's a really cool idea, but the problem with that measurement that we made was that it was based on recessional velocity, which is a different model. So, there's an issue there. So the whole thing that I'm working on at the moment is trying to remove that reliance on some other model that may not be correct, and to just from the principles of the data that we have, the observable data that we have from whatever telescopes, and then apply that to the model, and to ensure that using those two things, the model itself and the observed data, we can find the correct distances, both for the diameter of the hypersphere and the distances to the galaxies, and whatever else can come from that. But yeah, so the thing I'm thinking about now is the only feature that could possibly do that, which doesn't appear to be kind of relativistic in a sense that it can be moved up and down or in and out, changing the radius of the hypersphere or increasing the position of the galaxies further up towards the antipode or the projector point, would possibly be the cosmic microwave background radiation. So that's what I'm looking into at the moment, and that could probably give us the most accurate results, but it's very tentative at this point and tenuous whether that will actually happen. But it'd be great if it did, and it would be cool to it'd just be great to get a number, and say that's it, I'm done, like that's the number. And, someone else could take it from there, because at a certain point, you just get like, you just want it to end.
Oh, yeah. You are not putting in, considering gravitational waves, right?
No, not at the moment, no. But interestingly enough, I am thinking about doing some research into that. But from the perspective of gravitational waves, is it gravity wave? It is gravitational waves, yeah. From that perspective, no, to solve any of these problems, or the current problem that I'm discussing here with you, no, I don't see how you could apply it. But that's not to say that it can't be applied. Well, oh yeah, so another option was to use quasars, but I'm finding that the data on quasars, you see, everything is, like if we look at the angular distance, which is what is used to discuss this turnover point that occurs, and you know, you have the de Sitter space has no turnover point. It's just a smooth curve. So that's why it's not relevant to our universe. But these other ones do like have this minimum, which is where z is equal to approximately 1. And then the distances decrease again. But that's weird to say that the angular distance is decreasing. Surely they just mean that the angular diameter of the object is increasing. Doesn't mean that it's getting closer to us. But they seem to be suggesting that the angular distance is decreasing. The angular distance is, what is it, tan theta equals x divided by d, where x is the diameter measurement, the angular disk diameter, and d is the distance of the object from us. Now, see, there's two problems with that, because first of all, how are they calculating that distance? Well, they're calculating it through z redshift, which I maintain is the wrong way to do it, but let's ignore that. Oh, well, let's not ignore that, actually. Let's accept that possibly the distance is wrong. Okay, so if the distance is wrong, then their calculations for angular distance measurements will be wrong, without a doubt. But also, they could be wrong about the actual angular diameter of the object, because they don't know, if they don't know how far away it is and they don't know how big it is, you know what I mean? Because it could be like smaller but closer to us, or bigger and further away, and it would still look the same from our. And these are, it also seems a bit weird that these are, they don't actually seem to be actual measurements of objects. In some sense, it's some sort of mathematical creation that they have, which is very worrying. But so you have this angular distance. Then seems to be, it's a theta. It's some sort of degrees. It's based on distance. So I don't think it is actually a distance. They're not saying that it's actually closer to us. They're just saying it looks bigger. Its diameter looks bigger, and so that must be what they're saying. So the curve appears to go back up. So the graph they're using is terrible, because it seems to just suggest that these objects are closer to us than other objects, which are further away. And that just isn't right. I mean, in terms of the actual hypersphere, though, it is correct, which is weird. It's because, like, we're at the bottom of the hypersphere here, and then you go further and further away, objects get smaller and smaller and smaller, and then you reach around z redshift 1, like around somewhere around the equator, and then the sphere begins to curve back again. So, you know, they're further away, and then they kind of get closer in another sense when you project it back down. So, but yes, so, but if we just take it purely from that perspective, if we just map the galaxies onto the hypersphere using z redshift values or something, and then remap them back onto the hypersphere, or using this complicated method that I've come up with, where I could determine the absolute distance to the galaxies using redshift, provided we know the diameter of the hypersphere, what occurs is a completely asymptotic curve of all the redshifts, which can be plotted in a number of different ways, which kind of can be thought of as like a logarithmic curve or an exponential curve, if you like, where the closer to us, everything's like really close, 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 close. Then it gets further away, and then it goes exponentially up into like infinity sort of zones. So values like, so what that is saying is that we don't see this turnover in that sense. Everything just gets bigger and bigger exponentially. And so in order for that to work, then in order for this turnover thing, which presumably exists because they're talking about it and it must have been observed, we would need to start shifting the galaxies on the hypersphere so that they conform to that. And then we get into kind of that is a kind of a fine-tuning thing, or rather a better way of saying it, the theory becomes ad hoc, you know, you kind of, where you're basically moving things around so that it fits the data. And so that's a problem. That's a new problem that's come up with the model. So it could be the death knell for the model, but that's good, you know, because everything needs to die at some point. This thing can't go on forever. No.
Yeah, I mean, the sense that, you know, like you said, the closer thing. So there has to be an independent way of measurement. That's what I'm trying to come up. That you measure the diameter separately from what you measure the distance from us. So you have to independently measure and show that. Then you can say, is it nearby and larger? I mean, further away and larger, or nearby and smaller? This kind of thing you should be able to, gauge it.
Yeah, like if you could combine the actual angular diameter of these galaxies as they appear with respect to the celestial sphere, let's say, that surrounds the Earth. If you can get that, and maybe combine it with the data from the that I just recently calculated to do with absolute distance of galaxies based on Z redshift, and find some sort of sweet spot where these two things, like, they cannot be any other way. It has to be this way. So initially I was thinking like you could have some sort of program, like an app on your phone, which projected a augmented reality sort of visualization of the universe onto the night sky. And then you have your, like, a unit sphere, you know, with all of the galaxies on that sphere. And so that unit sphere has a diameter of 2, let's say 2 meters or whatever it is. And then you begin to increase so you're projecting, it's a hypersphere, and you're projecting that into a 3D tangent space onto the celestial sphere around you, also in a augmented reality sense. And then as you just with a slider, like, you increase the value of the diameter and see what happens to the galaxies. Do they start, at what point do they line up exactly with the angular diameter of the galaxies that we observe in the sky? But thinking about it, that's just not going to work. So it would have, because of multiple reasons that are quite technical. But yeah, like, maybe it's possible to combine it. And this, you know, we have a same problem with the Z redshifts. Like, there is an X variable that we don't know the answer to, and this allows us, it could be any size, you know, and it works out, the answers work out at any size, basically. But maybe if we have two things, we could work one against the other to get the correct answer, or not, because, you know, often if you have two X variables on two sides of the equations, I think on both sides, that equation you cannot solve. You can't solve it for those problems. So that might be the wrong way of going about it, and that's why I'm thinking that the best way might be to use, I think it's called Planck's law, the spectral radiance of the CMBR. You can also use spectral density, or not the energy density, but the results for some reason are coming out all weird. So the energy densities, there is no black body spectrum curve to that. The curve goes off the scale, so it's just like a curve like this. Anyway, we should leave it there, yeah, because it's 2.5 hours.
Yeah.
But this was an interesting talk.
Yeah, yes. Lot of different things, good things, yeah.
Yes. So we'll meet up next week. We're going to have M theory, is it?
Yeah, M theory. But I may be, as of now, I may only spend like half an hour, 45 minutes, then I have to leave because I have an appointment.
Right.
See.
Okay.
So
that's fine.
So I may just present that. Following week we can discuss.
Great. Okay. We'll leave there. I'll end the stream. So
okay, have a nice week.